joining me today. My name is Augustin and I'm from the Louvain-la-Neuve in Belgium. Today we're going to explore the direct and indirect environmental impacts of continuous glucose monitoring devices as a typical case study for mobile health technologies. And before I begin, and even because we are a small number today, feel free to interrupt me even online if you have any questions or if something is unclear to you. Let me provide a bit of context to this research. We're going to talk about mobile health. Mobile health, to make a long story short, in recent years, the ICT has seamlessly integrated into many applications, health applications that we thought previously unimaginable. And yeah, we've witnessed the rise of medical services and application due to the ICT, including mobile health, also abbreviated mHealth. To make a long story short, mobile health refers to miniaturized devices worn by patients that monitor physiological parameters of the body in real time. And these parameters are converted into useful data sent to an external smartphone app. For patients, this piece of information is really useful to better understand their own condition, and it enables also doctors to make data-driven decisions for better treatment. Some examples of mHealth devices include smartwatches, capsule endoscopes, cardiac monitors, and our today's case study, continuous glucose monitoring devices. And I actually brought one of them here for you to better see and better understand how it works. So basically, we have a miniaturized device, which is battery powered. So maybe I can show you. Actually, I've worn one. Oh, you've worn one, okay. So yeah, battery powered device is put on the arm with a plastic applicator. And basically, it will capture data for glucose concentration in the blood and transmit data over the air through to a smartphone. And people with diabetes usually say that it's a real game changer because they don't have to prick their finger anymore with the finger prick blood test, which essentially consists of pricking the finger with a lancet, collecting a drop of blood on a test strip, and insert this test strip in an electrical reader. However, when it comes to evaluating the performance of new medical technologies, the assessment remains focused on health outcomes and financial costs. Focusing on our case study here, CGM devices have proven to be more efficient than the finger prick blood test. However, as you probably understood, we're here today to talk about the environmental impacts, because the rise of mHealth technologies also goes hand in hand with an important deployment of connected devices that we know have a non-negligible environmental impact, mainly due to the plastics, electronics, transport, and sometimes batteries. In the case of the CGM, again, we have environmental impacts that are driven by the replacement rate of the device, which must be replaced every 10 to 14 days. Yet, so far, the scientific literature remains quite limited on the environmental impacts of mHealth devices. And environmental impacts are not considered in the health technology assessment. That's why in this research, we'll examine the environmental impacts of CGM devices through the lens of both direct and indirect environmental impacts. And really, the idea is to use CGM as a demonstrator for developing a framework that can be applied to other mHealth technologies. And we can integrate environmental considerations more systematically into health technology assessment. The direct impact will be assessed with a life cycle assessment, and we will also identify the main advantages and the main limitations of such direct impact assessment. From there, we will then extend the analysis to indirect impacts and how we propose to model them in the context of this work. And finally, this presentation will end with a brief presentation of the current state of the framework. About LCA, I don't know if I can remove this small...
Yes.
Yeah, how?
Yeah,
That's perfect. Yeah, that's perfect. Okay, about LCA. The starting point of an LCA is always an environmental question that relates to the impact of a specific function. In our case, the question is twofold. First, what are the direct environmental impacts of CGM devices? And second, how do they compare, how do they relate to those of the finger prick blood test? We define the CGM as alternative A and the finger prick blood test as alternative B. The functional unit for which we'll assess the environmental impact is defined as monitoring the blood glucose levels of types 1 and type 2 diabetic patients in Belgium over the course of 1 year. To meet this functional unit, in alternative A, we need 31 CGM devices due to the replacement rate. In alternative B, we need, on average, according to our assumptions, 700 test strips and needles. Needles, the lancet, I mean, to prick the finger. And 1/3 of a reader. Why 1/3? Because the reader lasts for more than 1 year. So we need to allocate the impacts of the device proportionally to the functional unit, which is defined over the course of 1 year. Based on specific reverse engineering techniques, we were able to collect data about components, materials, transports, and energy consumption to model these reference flows. And this data was used to build what's called the foreground system. That's part of the life cycle model, which is specific to our case study and that produced the reference flow. And then we connected the foreground model to what's called the EcoInvent database, acting here as the background system. And really, it was useful to scale the environmental flows related to each EcoInvent activity to obtain, at the end of the day, the total amount of environmental flows that relate to our reference flow, so to say, to our functional units. This slide presents the results for 5 out of the 16 impact categories from the EF 3.1 impact method. The first key takeaway is that alternative A, the CGM device, has higher direct environmental impacts than alternative B, the FPBT test, and this across all categories. The second takeaway is that the main drivers for impacts are the plastic, mainly in the applicator, because it's quite heavy, as well as the integrated circuits, so these active electrical components that convert blood glucose level into digitalized data. In this LCA, we also wanted to explore some eco-design scenarios. The first scenarios is the reference one. So as defined earlier, 31 devices used per year. Scenario A1 makes the assumption that plastic use is reduced in the applicator. Scenario 2 goes even further, making the assumption that the applicator could be reused thanks to design changes. And finally, scenario A3 makes the assumption that the device itself could be reused, and only the needle, which is not here on this particular device, but the needle is the only part that is replaced. Let's jump to the eco-design results, scenario analysis. We can observe that we have a steady decrease from scenario A0 to A3. From A0 to A1, so A0 to A2, this is mainly due to the decrease in plastic use. And from A2 to A3, this is mainly due to the fact that we reuse high impact electronics. This could have been the end of our LCA, but in my thesis, I'm also really interested in uncertainty analysis. And I wanted to model what's called parameter uncertainty, because when we construct the foreground model, we have some uncertainties about specific values. For instance, I challenge you to determine the exact route, shipping route that this product has traveled from Asia to here. It's almost impossible to determine close to the kilometer. You have the right order of magnitude, maybe 1,000 or maybe 5,000, but you are not sure, basically, you lack knowledge about this data. And to cope with this, we attribute probability density function to each key parameter in the model, and this allows us to propagate this input uncertainty to output impact estimates and obtain, at the end of the day, a violin plot for each of the scenarios. Hopefully, luckily enough, we can still observe this steady decrease from one scenario to the other, but now we're only able to make conclusion up to a given probability. For instance, here, the probability that the impacts related to scenario A3 are lower than alternative B, the FPVT test, is almost 70%. And this essentially brings more robustness to the conclusions that we can draw from our LCA. Okay, so we have been able to draw the following conclusions. CGM devices have higher direct environmental impacts, and introducing reuse significantly reduce CGM environmental impact, direct impact. These conclusions are really helpful to support decision-making at a small level, at the patient level, because patients can make eco-conscious choices based on the impact estimates of this LCA. And also, the fact that introducing reuse reduces the impact can guide eco-design effort for the engineers that design this product. However, we still lack some insight into environmental impacts because we miss some information about the impact that could arise from interaction between this technology and the healthcare system. A very concrete example, CGM, because of the better monitoring, could reduce the number of emergency hospital visits because you better monitor your glucose level. Or more broadly, we miss the insight into environmental impact that could arise from the interaction between this technology and the broader socio-economic organization, or so to say, society. Again, a very concrete example, there are some models that are targeting a part of the population that doesn't have diabetes. So there is this new technology that is targeting the wider population without
a rebound effect, essentially.
It's essentially a rebound effect. So that's why we need to have a look at the indirect impacts. That's the true motivation for the impacts, at least at the society level. At the healthcare level, it's a bit different. But I'm jumping into those results in a few moments. Before I introduce the indirect impact, there is a small plot twist in this presentation. We have to make a small detour into health economics. Health economics is a specialized branch of economics dedicated to optimizing healthcare resource allocation to meet the population health needs. And in health economics, in other words, we study how to maximize health outcomes for a given limited budget. To quantify costs and outcomes in health economics, the models often break down disease progression into different discrete health states, with each state having its own associated cost and outcomes. The model simulates the journey of a cohort of patients over time through these states, and the model accumulates cost and outcomes for each procedure, and they are then aggregated at the end of the simulation to obtain a given cost value and a given outcomes value for your reference procedure, which are here finger prick blood tests or CGM devices. And you can compute in a cost effectiveness plane the incremental cost effectiveness ratio. That is the increase in health outcomes that you have when you put an additional dollar or euro or monetary value in general. Okay, that's it for our small detour into health economics. Now let's imagine that we can add environmental impact to each of these states. Then we will augment the cost effectiveness plane to have this three-dimensional representation, having environmental impacts at the third dimension. And so to say, the distance between this plane with reference having this impact and this point, I'm too short to point this point, with the, another procedure having different impacts, basically the distance could reveal some orders of magnitude in impacts, indirect impact between the reference procedure and the comparator. And finally, we still miss the indirect impact at the scale of society. And for this, we believe, and it's based on a paper from last year's conference, that systems thinking could offer a valuable approach. Systems thinking is a way of making sense of the complexity of the world by looking at it in terms of wholes and relationships, rather than splitting down into parts. One widely used tool in systems thinking is the causal loop diagram that helps visualize how variables influence each other through the causal relationships. And what makes this approach relevant in this particular case, is flexibility, because causal loop diagrams are not limited to healthcare variables or environmental variables, but we could also integrate economic variables, social variables, and so on, to have a better representation of the system dynamics at stake. As part of this research, we've developed a first causal loop diagram, which is not in the paper, but it's a work in progress. So we have, in the meantime, developed the first causal loop diagram to map the system dynamics associated with CGM devices. There's no need here to take a deep dive into each of the variables, but I wanted to highlight that we have identified, for instance, this positive feedback loop that can drive negative impact as e-waste or resource use, but in the same time drive positive impact. So such tool is really helpful to visualize system dynamics. This brings us to the final slide of this presentation, which is kind of a summary for the multi-level framework. Our LCA offered valuable insight into direct impact, and also informed decision-making at the patient level or the design engineer level. And approaching the indirect impact required tools from other disciplines, so it's an interdisciplinary framework, like health economics, like system thinking. And these tools can really inform decision-making at broader level, at the healthcare system level, at the more political level. And what I find particularly interesting here is that each tool offers a complementary perspective, revealing dimensions of impact that the others may overlook. But there is drawback because we need a lot of interdisciplinary knowledge and a lot of data, for instance, product data, patient data, clinical data, market data, to really feed this framework. And finally, it's important to emphasize that the objective of this framework is not to obtain a net balance between direct and indirect impacts and to say, okay, the positive indirect impacts really outperform the negative direct impacts. So it's rather to have this comprehensive approach to environmental impacts and ultimately provide more insight to decision making. And that's the end of my presentation. Sorry for the small delay.